Hey everybody, I'm going to be going over the first part of 5.7, going through all the examples with you if you wanted to watch this. The first part of 5.7 is about using the natural logarithm, looking for things like 1 over u du is the natural log of the absolute value of u. If you recall why we're using the absolute value, it's because for our function that we're integrating, our domain is u just isn't allowed to equal 0. So we want our domain for this output to be u doesn't equal 0. And the absolute value will then allow us to plug in or have negative things in there. And what really we're looking for now that we're doing u substitution is this idea, it's this idea that we're going to have some function and its derivative. And that function is going to normally be in the denominator, its derivative will be in the numerator, and we'll be able to utilize the natural log to take those integrals. So let's take a look at what's going on there. This first example, you see in the denominator we have something quadratic. In the numerator you see we have something linear. So if you were thinking u substitution, you might say, well, x squared, not plus, minus 3x might make sense because when we take the derivative, we get 2x minus 3 dx. And would you look at that? We can replace that thing perfectly with du. Everything that I highlighted, we can now rewrite as du. What's left in the numerator after we replace? Well, 1. And then it looks like we're calling the bottom u. And at this point, integrating 1 over u, we get natural log of u plus c inside the absolute value. And then, of course, we need to rewrite our answer in terms of x. So we have the natural log of the absolute value of x squared minus 3x plus c. All right. Similarly for the next one, I'm noticing again, I see something squared in the denominator. I'm seeing a linear term up top. It's making me think u substitution might be our friend again. So if I call u 3x squared plus 1, taking the derivative, we get du is 6x dx. And if we're trying to replace a 3x, you might think to yourself, well, if we divide by 2, we get 1/2 du equals 3x dx. So now we can replace that stuff highlighted with 1/2 du. What's left on top when we do that? 1. We're substituting our denominator with u. The only other thing we can't forget our bounds. Changing to u, let's change our bounds so they match with u. So u of 0 equals 0 plus 1. It's 1, and u of 3 equals 3 times 3 squared plus 1, which is 28. So let's put those new bounds onto our integral. Just like above, when we are integrating 1 over u du, we get the natural log, absolute value of u. I'm not going to write plus c this time because we have a definite integral. We're just going to evaluate at our bounds using the first fundamental theorem of calculus. We have that 1/2 out front, natural log of 28 minus natural log of 1. And if you might recall, natural log of 1 is 0. So we can write our answer as 1/2 natural log of 28. You'll notice that I don't have the absolute values written anymore, but you don't need them because 28 is positive. All right, this next problem, this is where we start getting a little tricky. You might say, well, look, right there, quadratic. Down underneath we have linear, so maybe our idea is to, this isn't erasing very well, sorry about that. maybe the idea here is to make u x squared plus 7x minus 3, taking the derivative, du equals 2x plus 7 dx. And there's a couple things wrong with this. First of all, getting 2x plus 7 to match x minus 2, not going to be doable. It's kind of looking like. The other problem is, oops, again, I'm not getting the eraser right. If I'm trying to replace this x minus 2 dx, this is in the denominator. This is not in the denominator. This is a numerator thing. So here's the problem. If I was really trying to replace the stuff highlighted, I'm really looking to replace 1 over x minus 2 dx. And taking the derivative of something x squared up here is never going to give me x minus 2 in the denominator. So it's looking like u substitution as is isn't going to work out. So what we need to do, something that you might recall from pre-calculus, we need to do some long division. I think we might have done this once or twice together in class. We're going to take our denominator, we're going to divide that into our numerator. I'm hoping you kind of remember how this works. What do we need to multiply to x to make it 2x squared? That's 2x. We're going to multiply that 2x to both of those. And do not forget to subtract. 2x squared minus 2x squared cancels. That's on purpose. 7x minus negative 4x, that's 11x. And we're going to drop down the next term, the minus 3. Now, we look at 11x and we look at x. What do we need to multiply to x to make 11x? That is plus 11. We take our plus 11 and we multiply it to both of those, so we get 11x minus 22, but of course we are subtracting. 11x minus 11x, gone. Negative 3 minus negative 22, watch your signs. That's 19. And at this point we would have to divide x by something to get 19. We don't want to do that. But what do we do with this remainder? When we're rewriting our function, we're going to take our remainder and write it over the thing we are dividing. So we can actually rewrite this integral as the integral of 2x plus 11 plus 19 over x minus 2 dx. Now it looks like there's more to do, but we know how to integrate all of these parts. So that's nice. How do we integrate 2x dx? That's x squared. How do we integrate 11 dx? That is 11x. How do we integrate 19 over x minus 2 dx? You might be able to see this without writing a lot of extra steps, but if you're like, ooh, this looks a little tricky, I'm going to tell you, use a little u substitution here. U equals x minus 2, so du equals dx. So we can rewrite this integral. I might pull the 19 out in front of the integration symbol, just so that it looks familiar. We have 1 over u du, which is 19 times the natural log, the absolute value of u. So, subbing back in our x stuff, we get plus 19 natural log of the absolute value of x minus 2. And of course, we cannot forget our plus c after all that. So, we're going to write a note to ourselves at the top of the next page here. But looking at this problem one more time, sorry about that. Looking at this problem one more time, you will notice our bigger power on top. Okay? So when you flip over, note this thing at the top of the next page. If the degree of the numerator is greater than or equal to the degree of the denominator, what are we going to do? We're going to use division. Long division, synthetic division, to rewrite the integrand. So you'll notice on the next page here, the next two problems are identical. So I'm going to go through them two different ways of doing the same thing. The first way is going to be a little bit more familiar with what we were doing before. Taking a look at maybe how to do this with u substitution, you might think to yourself, well, let's take the harder stuff, the stuff that's got some pluses and minuses. Let's make that u. So if u is 2x minus 4, then du is going to be 2 dx. Now the problem with that is rewriting 1/2 du equals dx. We still have this x that's floating around up top. So what did we talk about in cases like this? How do we get rid of that x? Well, if we rewrite the u equation and solve for x, we can then replace x with that. So how could we rewrite this integral in total? I cannot forget this 1/2 with the du. Don't forget that. Don't forget that. So 1/2 comes out to the front. On bottom we get a u. At the back end we get a du. And what are we replacing x with? I might write it as u over 2 plus 2. Why is this easier than what we started with? Because we can break this up into two different fractions. So we get 1/2 integral u over 2 divided by u is the same thing as u over 2u, plus, and then we have 2 over u, which actually, when we're done simplifying, doesn't look all that bad. We get 1/2, integral of 1/2 is just 1/2 u. Integral of 2 over u is 2 natural log of u. And then we cannot forget our plus c. Distributing the half, 1/4 u plus ln, the absolute value of u plus c. And then, of course, I need to rewrite this in terms of x's. So that's 1/4 2x minus 4 plus the natural log of 2x minus 4 plus c. So there's our answer right there. Let's see this done in a different way. Maybe you like this way, maybe you're cool with it, but let's check out another way. Because the degree on top and bottom is the same, we can do a little bit of division here to rewrite the integral. The integrand, I should say. What do we multiply by 2x to get x? That would be a half. Multiplying a half to both of those, we get x minus 2. And again, one more time, please don't forget we are subtracting. So 0 minus negative 2 is 2. So how can we rewrite our integral? That would be the integral of 1/2 plus 2 over the thing we are dividing, which is 2x minus 4 dx. You might look and say, well, I can actually simplify that second piece right there. I can take a 2 out of everything, so it's 1 over x minus 2 dx. And then you might be able to come up with this on your own. Integral of 1/2 is 1/2 x. The integral of 1 over x minus 2, I'm going to skip the u sub for this part right here and write the natural log of x minus 2. See if you follow. If you don't, try the u substitution for that. Now you might be saying, Mr. G, the answers you got for the first and second are different. So let me try to convince you they are the same. Let's take this top one. When I multiply the 1/4 in, we get 1/2 x minus 1 plus. I'm actually going to factor a 2 out of here. 2 times x minus 2 plus c. Well, you might notice that now you can see the 1/2 x. What about the natural logs? If you remember our log properties, you might recall we can break up the logarithm into two different pieces. And right there you might notice Well, there's our natural log of x